Bismillah ar-Rahman ar-Rahim. So, yeah, today we are going to start the number systems lecture or unit, all right, of this course. And this lesson's objectives are, so let me say something before I start. Maybe some of you haven't, my name is, so if your name is not in the list or you come late, write your name and ID on the chat, okay? And I will take care of it afterwards, okay? So, yeah, I'm not going to reopen the forms. I'll do it myself. Okay. So this lesson, as I said, okay, has a number of objectives. Actually, it's 6 objectives, and you will learn how to convert numbers, okay, from any base to decimal, okay. This is one objective, from any base to decimal, and the second objective is from any decimal, from decimal to any base. And we distinguish between 2 cases here: from decimal, from integer decimal to any base, and from fractional decimal to any base, because the algorithm is different in each case. And then we will study how to convert from binary to octal or hexadecimal and vice versa. Okay, and then we'll learn about some important properties in number systems. We will also learn about how to perform addition and subtraction of unsigned binary numbers, okay, as well as hexadecimal numbers. And then we will learn about binary coded decimals and ASCII characters and parity codes. Okay, so these are the objectives of this multi-lecture lesson. Okay, maybe it will take 2 or 3 lectures. So we start by objective number 1 today. But before that, we have to introduce some concepts before we are able to convert numbers from any base to decimal. We have to introduce some concepts. First concept that we would like to introduce is the radix or the base. Okay, so the decimal numbers that we know have how many digits? Who can tell me how many digits do they have?
10 digits.
10 digits. Excellent. So the digits are from 0 up to 9, right? And the size of this set is 10. Okay, and this is why we call our system, we call it a decimal system, because it contains, decimal means عشري بالعربي, okay, يعني في 10 there are 10 unique digits in it. Okay, so there are 10 digits and it's a decimal system. It has 10 digits, 10 possible digits for each place. All right, and so we call this 10 here, we call it, it's called the base of the number system. The decimal number system has a base of 10. Okay, whereas the binary number system, how many possible digits in the binary number system?
2.
Either 0 or
2.
1, which is 2. Excellent. Yeah, so the base of the binary is 2. Okay, the base in the binary number system, we call the base is 2. Okay, the binary number system has a base of 2. However, it has a name. Okay, it's called the binary number system. And if we say binary number system, we don't have to mention the base. Okay, the base is by default 2. Okay, even in the decimal, the base is 10 by default. Okay, it's well known. As well as hexadecimal, the base is well known to be what? So in hexadecimal, we have 0, how many digits do we have? How many possible digits? 0, 1, 2, up to 9, and then we have to have more digits, okay? Because the base is 16 in the base of in the case of hexadecimal digits. So how to represent the value 10 or the digit 10 in hexadecimal? You have to represent it with a single symbol, okay? So we are out of digits here, so we use letters rather than digits to represent numbers beyond 9, okay, or digits beyond 9. So the first letter, which is A, represents what? Digit 10 of hexadecimal, and then B represents digit 11, and then C digit 12, and then A, B, C, D 13, E 14, and then F 15, and then that's it. Okay, so it has how many digits?
16.
16, and therefore its base is 16. Okay, notice that the base is always one greater than the maximum number, the maximum digit. Okay, it's always that. So 16 is greater than F, which is 15. Okay, all right. So this is the concept of the base. Sometimes the base is called interchangeably, it's called the radix. Okay, it's the same two names for the same thing. Okay, radix or base. Okay. So this is the concept of the radix or the base. Okay, we have covered it. So it tells you how many digits does the number system have. Okay. The radix point, concept number 2, the radix point, okay, is related to, let me erase this now. We understand the concept of the base, okay. The radix point is something, so if I tell you, using the number system that we are familiar with, which is a decimal system, I say 100 or 1,512, okay, then I say, well, there's a fraction of 61 here, okay, and it is in decimal. This is a decimal number system. What do you call this thing here? Point. Excellent. It's a point, right? It's called in specifically it's a decimal point. Okay. Why do we call it decimal point? Because we are dealing with decimal number. Okay, a decimal number. So this is called a decimal point because we are dealing with a decimal number. And how do we indicate that we are dealing with a decimal number? We surround the number by a bracket and write down the base on this corner here. Okay, so this tells you that the number is in decimal. However, if it is another base, like for example this one here, okay, so this is a binary number. Can we still call this point a decimal point?
No.
It's not a decimal point, right? It's a binary point, right? It's a point that belongs to a binary number. Okay, so this is called the binary point now. Okay, and in general, if you have radix r, okay, it's going to be called the radix point. Okay, so even this one is called the radix point, okay, because the radix point is general. It's a general term. Okay, all right, so any question about radix point or decimal point? Okay, so what do we call this one here?
Hexadecimal point.
Can you raise your mic volume, please? Because I can't hear you.
Hexadecimal point.
Decimal point?
Hexadecimal.
Hexadecimal point. Excellent. Yeah, it's a hex point. Okay, hexadecimal point. Right. Okay, you understand that I'm just using a shorthand of hex to represent hexadecimal numbers, hexadecimal keyword. Okay. All right. So we understand the concept of Radix point now. The next thing is the most and least significant digit. Okay, so I have, for example, this number, 2,152. Okay, and this is a decimal number. Okay, we call this digit here, call it the most significant digit, MSD. Okay, and this digit here, we call it the least significant digit. Okay, why? Any idea why? Why does this digit have more importance or more significance than this digit?
Because it's bigger, larger.
Yeah, its magnitude is larger. This has a magnitude of 2,000, whereas this has a magnitude of 2 units only. Okay, so the leftmost position is called the most significant digit, and the rightmost position is the least significant digit. Okay, now this is when we talk about any number system. However, for binary, okay, there is a specific name. Okay, digit, we call them a specific name, which is what? I'm sure that you guys know. A bit, right? A bit is a binary digit. Okay, so in case of binary, if you have 1 0 1 1, okay, this is going to be called the most significant what? Bit. Okay, and this is going to be called the least significant bit. Okay, all right, I think we are now ready to discuss the conversion algorithm from any base to decimal. Okay, so this is how we can convert this number here, generic number, all right, that has n fractional digit, in integer digits, I'm sorry, okay, and m fractional digits. Okay, how do I know? Because they are separated by the radix point. Okay, and I'm representing the digits. Each digit I'm assigning it a subscript so that I know them. Okay, so this is digit number n minus 1 and then n minus 2. So what is the most significant digit here?
N minus 1.
Yeah, d sub n minus 1. Yeah, and if I talk about only the integer part of the number, then the least significant digit is d sub 0. However, if I talk about the whole number, then the least significant digit is going to be d sub minus m. Okay, so the number has m fractional part digits and n integer part digits. Okay, and it is in base r. Now, in order to convert it to decimal, I simply use this formula here, or this algorithm. I just sum these products, digit number I into r, which is the radix, times r to the power I. I'm sorry, it's r to the power I. And I goes from minus m to n minus 1, okay? Because we have m plus n digits, okay? All right, so you apply this algorithm and you're done. You're done with the conversion. That's it. Okay, so let's take an example to simplify this. Okay, so just for the sake of, you don't have to do this when you convert, but for the sake of sanity checking, okay, I want you to see this number here and tell me what m is, and n minus 1 is, and r is. Okay. So what is m now?
1.
Can you say it again? I didn't hear you.
1.
1. M is 1.
Yes.
So what does that mean?
I think it's two.
Most significant number.
No, it's not. This is d sub minus m. Okay.
Least significant bit.
Yeah, it's basically the least significant bit. No. All right. So you have to distinguish between the d sub minus m and m itself. You have to distinguish between them. D sub minus m is the least significant digit. It's correct, or bit. Okay. But m itself represent what?
The number 2 in this example.
Come again?
2.
After
Yeah,
the
it's
vote.
2. It's the number of fractional bits. Yeah, it's 2 in this example. So n minus 1 is 3. Okay, because we have d sub 0 up to d sub 3. This is d sub 0, d sub 1, d sub 2, d sub 3, right? This is n minus 1. Okay, so we have n equals 4. Okay, n minus 1 is 3, n equals 4. So n is the number of integer digits, okay, or bits. You see that? Okay, so what's that? Okay, so this is 3, and r is what?
The base.
Yeah, 2, the target base, or the source base that we'd like to convert from. So now for conversion, you just apply this algorithm. So the 1 is multiplied, this one here is multiplied, this one I'm saying, is multiplied by 2 to the minus 2, okay? And then the 0 is multiplied by anything is 0. I don't have to write it, okay? And then plus, this one is multiplied by 2 to the 0, so it's 1, okay? And then this one is multiplied by 2, so this is going to be 2. And this 0 is multiplied by anything is 0, okay? So I don't have to write it. And then this one here is multiplied by 2 to the 3, which is 8. So this is what? 11.25. So this is 1 over 4, right? Okay, so 1011.01 in binary is equivalent to 11 or 11.25 in decimal. Okay, cool.
Can you repeat it again, please?
Yeah, sure. Let me just be more verbose so that you guys so I'm going to apply the algorithm as is now, okay, with the zeros, and let me just make my pen a little thinner, okay? So I'm going to start from here, okay? I'm going to start from here. So it's the value is going to be 1 times what? 2 to the minus 2 plus 0 times 2 to the minus 1 plus 1 times this one here. 1 times what? 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 to the 2 plus 1 times 2 to the 3. Okay? It's just a direct application of this formula here. Okay?
Yes.
We start from minus m all the way to n minus 1. Okay? So we start from minus 2 here all the way to 3. From minus 2 all the way to 3. Okay? Do you see that?
Yes.
Yes, yes.
Okay, and then you just collect the terms and find the answer. That's it. And you'll find it that it is 11.25 in decimal. Okay, so I'm not going to include my answers in the sheet here. You can find my answers in the videos. Okay, so for this now, let's see whether you get the idea or not. What is n for this example?
1.
1. Excellent. And n minus 1?
3.
3.
Okay, and r?
60.
16.
16. It's not 60. Okay, it's 16. All right. So now apply the algorithm. F has a value of 15 times 16 to the minus 1 plus what? C, which is 12. Okay, times what? 16 to the 0
16.
plus 0 times 16 to the 1 plus B, which is what? 11 times 16 to the 2 plus 1 times 16 to the 3. And then you just compute these and then represent the answer. Sometimes if it contains something like this, then we will tell you in the exam or quiz that we only want 2 decimal digits, for example, in the fractional part. Okay? So you must account for that. Okay? All right. Now let's move on to more cryptic or tricky examples. Okay? So here is an example. I'm going to do in the previous section I did this. Now I'm going to do the other one. Okay? Which is this one. Okay? If you want to see how I did this, go back and look at the video of the other section. Okay? So I'm going to do this, which is an equation here. Okay? 2, 4 to base r plus 1, 7 to base r is equal to 4, 0 base r. And you are required to find the value of r that satisfies this equation. Okay? Obviously, if you if r is decimal or it's 10, then the equation is not satisfied, right? Because 24 plus 17 is not 40. Okay? So what you do is that you convert every number in the equation to decimal. Okay? So what is 2, 4 base r in decimal? Just use the algorithm. Okay? It's 4 times r to the 0 plus 2 times r to the 1, right? Which equals 4 plus r, right? What is 1, 7 base r? Come on, guys.
7 times r to the 0.
Yeah, 7 plus. We did it here, so we don't have to repeat the
Plus 1 to the times r power 1. Yes.
Yes, excellent. Which is 7 plus r. So 4, 0 is 4r, right? So we have an
Yes.
equation. We have a linear equation, a very first order equation, 4 plus r plus 4 plus r, this one here, 2, 4 plus 1, 7 plus
Isn't it
7
2R?
plus r is equal to,
Doctor,
yes,
the first one shouldn't be 2R.
2R,
For-
is it?
yes, excellent. Yeah, it's 2r. Okay?
I think the second one, the same.
No, the second one is 1, 7. Okay, let's do the second one in a long way. Okay, so it's going to be 7 times r to the 0 plus 1 times r to the 1, which is 7 plus r. Okay, so this is 2r here. Okay, and we have, so we in this side we have 2r plus r is 3r, and then here we have r. Okay, so r equals what? 11. So the base is 11. Okay? You get it? You can double check that by converting the numbers to decimal, okay? 24 base 11, and then 17 base 11, and then 40 base 11. Make sure that 24 base 11 plus 17 base 11 equals 40 base 11, all in decimal, okay? All right, so this is trivial, okay? Now this is another trick, okay, in which we have a quadratic equation, okay, and the coefficients of the quadratic equations are written in different bases here. So this coefficient 1 is in base R1 and 2 is in base R2, okay. And you are given the solutions to the equation, which are two solutions, 3 and 6. So the purpose here is to find R1 and R2. Okay, that satisfy this equation. How do you proceed here? Given the solution, you can plug in the solution into the equation one time to get one equation, and then plug the solution again to get another equation. The equations are in R1 and R2. So I'm going to show you how to get one equation and then leave the rest to you, okay? So for the solution for x equals 6, for example, let's say, because I did x equals 3 for the second section, for the previous section, okay? You can combine the two videos and see for yourself. So we have x squared, which is in decimal, it's going to be 36, okay? Minus 1 base r. What is 1 base r? It's r1 base r1, I'm sorry, plus 1, right? Isn't it?
Yes.
Okay, times what? Times x, which is 6, plus 2 r2 plus 2, and that equals 0, okay? So if you collect the terms and rearrange the equation, you get a nice equation in R1 and R2, okay? So we have here a 6 minus 6 and plus 2, so minus 4. So 32. So we have 32 on the other side, minus 32. So it's minus minus 6 R1 and plus 2 R2, or if you multiply by minus 1 and divide by 2, you get 3R1 minus R2 is equal to 16, right? This is your first equation. You find the other equation and then solve two equations, two unknowns, okay? You got it? Okay, this is the furthest or the trickiest trick in this algorithm, okay? Now, if you don't have questions, I'm going to move on to the next subject, okay, which is conversion from decimal to any other base. And we are going to discuss today the integer case, okay? Okay, so the algorithm is simple here. We just keep dividing by the target base. You want to convert your decimal to binary, for example. You keep divide by 2, okay, until you get a quotient of 0. And in the meanwhile, you keep record of the remainders, which will constitute your number in the target base. Okay, let's see an example. So in this example, I would like to convert 156 in decimal to binary. Okay, so simple. I just keep dividing 156 by 2. I get 78 with a remainder of 0. Okay, and then I take the 78. I take it here. Okay, and then divide it by 2. Now I get 39 with a remainder of 0. Okay, And then I take the 39 again and divide it by 2. I get 19 with a remainder of 1. 19 divided by 2 is 9 with the remainder of 1. Okay. And 9 divided by 2 is 4 with the remainder of 1. 4 divided by 2 is 2 with the remainder of 0. 2 by 2 is 1 with the remainder of 0. 1 by 2 is 0 with the remainder of 1. So we kept record of the remainders as we go. We stop when the quotient is 0. Okay. So the order at which we collect the bits, okay, is going to be from bottom to the top. So this is going to be your most significant bit, and this is going to be your least significant bit. Okay. So 156 in decimal is going to be 100. Follow it here. 100, and then 111. 0, 0. Okay. All right. Now let's take a more involved example. The binary is dividing by 2 is simple. So let's divide by 8. Okay. So we would like to convert 175 in decimal to octal. Okay. So it's the same. So what is our target base here? Guys, did I lose you?
Base 8.
8. Yeah. So pay attention, please. Okay. So 175, I start dividing by 8 and collect the remainders. Divided by 8 is what? I have to do the division, right? 8, 175. Okay, who can tell me what is the quotient here? It's 2. So I'd say, well, 16, and the difference is 1. And then I pull down the 5. Okay, so this is going to be 1 times 8 is 8. Okay, and then
0.875.
7. Okay, so this is the remainder, and this is the quotient. So I have a quotient of 21 and the remainder of 7. So this is quotient, remainder. Okay, then I take 21 and divide it by 8. I get what? Do I need to do the division? No, it's actually 2. It's going to be 2. This is trivial, right? 2 with the remainder of
5.
5. Excellent. Yeah. So I take the 2 now divided by 8. Answer is 0 with the remainder of 2. Okay. So I collect the digits this way. Okay. So my 175 in decimal is equal to 257 in octal. Okay. Okay. So now we are going to do a hexadecimal example. Okay, so we would like to convert 715 to hexadecimal. Okay, so the first step is to divide 715 by the target base, which is
16.
16. Excellent. Yeah, so 715 by 16. Okay, and the answer to that is, I have 4 here. Okay, 4 times 16 is 64. Okay, subtract. What do you get? You get 7. Okay, and then you pull down the 5. Okay, so 75 again 4. Okay, 64. Okay, which is 1 and then 1. Okay, so this is the remainder and this is the quotient. So the quotient and remainder. Quotient is 44 and remainder is 11. Okay, now we take the quotient and divide it by 16 again to get what? 2 times 16 is 32. So 2, okay, 32 to 44 is 12, right? Isn't it, guys?
Yes.
Are you
Yes.
challenged by this?
Maybe we are a little bit rusty in the long division part.
Okay, so you want me to repeat this one here? Okay, let me just repeat it in a slow manner. Okay, so 715, okay, divided by 16. Okay, so first of all, you take the 7, which is less than 16, so it doesn't work. So you have to take 71. Okay, 2 digits. Okay, so 71 by 16. Okay, what is the integer part? How many 16s in 71? How many integer 16s in 71? There are 4, right? Because 4, if you multiply 5 by 16, you get more than 71. So it's exactly 4. Okay, so 4 times 16 is 64. Okay, and then you subtract that from 71 exactly. Okay, you get what? You get 7. Okay, 71 minus 64 is 7. And then you pull down the 5 here. Okay, so you get 75 now. So how many 16 in the 75? Again,
4.
it's 4, yeah? So you have 64 here. And then the difference is going to be 11. Do you get that? Okay, now let's do 44 by 16. So 44 by 16 is trivial, okay? Because you cannot really, it's 2. It's going to be 2, and the answer here is 32. So because if you multiply it by 3, you get 48, right? Which is more than the number. So you cannot have 3, okay? 32, and the subtraction here is going to be 12, okay? Which is what we got here, okay? So 12 is less than 16, so I can stop. Okay, so this is my remainder, and this is my quotient. Okay, you get that?
Yes.
Okay,
Yes.
now we take the 2
Doctor,
and divide it by 16. When how many 16s in 2?
0.
0. Okay, and so the remainder is the number itself. So it's 2. Okay, so that's a fun fact. So I really advise you to review your division. Okay, go back to elementary school. Okay, and review it. It's worth doing that. Okay, so now,
Doctor,
yeah, question.
from where we take the 16?
Which 16? This one?
Yes.
Yeah. So remember that the algorithm that if we want to convert a decimal number to another base, we keep dividing by the base. Okay, so here we are converting to hexadecimal. What is the base of hexadecimal? It's 16. So we keep dividing by 16. Okay, so now this is the, you get it now?
Yes, yes.
Okay, so we collect the digits this way. So the number 715 is what? What is this number in hexadecimal?
2.
So the first digit is 2. Second digit is,
C.
raise your voice, I can't hear you.
C.
C, excellent. Why? Because C is equivalent to
12.
12. Okay, and then
B.
B.
B. Okay, because B is equivalent to 11. 16. Don't forget to write the base. Okay. Okay, so
Doctor,
yeah.
well, what if we have a radix point?
So you want to convert a fractional decimal to another base.
Yeah.
Yeah, that's the subject of next class. Okay, remember that we are doing here what we are doing here, integer case. Okay, next class we will cover the fractional case. Okay.
Okay.
Yeah, because it uses a different algorithm. So now let me summarize what we have done in this class. Okay. So what we did is to discuss how to convert numbers from any base to decimal. Okay. Including fractional and integers. This algorithm works for both. Okay. You don't have to differentiate between fractional and integer parts. Okay. So this algorithm works for both. Okay. So, and then we discussed some of the concepts. Remember them, please. Okay. About the conversion process and number systems in general. Okay. So we said that if the number is contains n digits, in integer digits, and m fractional digits, where the digits are symbolized like this: d sub n minus 1, all the way to d sub 0, point, d sub minus 1, all the way to d sub minus m to base r, then the integer conversion of this is here, is this one here, the formula, the summation formula. And we did two examples, straightforward examples, okay? And then we did tricky examples. You can look this up in the video of the other section if you want to see how it's done, or do it yourself, okay? It's easy, okay? Just convert every number to decimal, and then you will get to find r, okay, by solving the equation, okay? And then we did this equation as well, and then we did the quadratic equation, okay? And then we moved on to converting numbers from decimal to any other base for the integer case. We did an example on decimal to binary conversion, and then decimal to octal, and then decimal to hexadecimal. Okay, any question? I'm going to upload the notes without the solution, okay? So I'm going to erase the solutions here. If you want to see the solution, you watch the videos, okay?
Doctor,
Yeah.
where can I find the recorded videos?
Okay, this is an excellent question. Okay, so go to the Blackboard. Go there. Right. So this is not your section. Your section is this one here, section 4. Okay, and lecture recordings. So this is your section. Okay, I haven't yet uploaded this lecture. Okay, this is your section. It contains only lecture 1. Okay, and then the other section is here. Okay, if you want, you can check the lectures of the parallel section here. Okay. Okay. So even this one I haven't had time to upload because actually the lectures are back to back. Okay. I'm going to upload both, inshallah, today, and you can have a look at both. You got it? So yeah, and then I'm going to upload the notes, the class notes, in here. Okay. But the class notes will not contain, they will not contain the solutions. Okay, so I'm going to erase all the solutions, and then you have to watch the videos in order to see the solution. I advise you to try the solutions yourself and then watch the videos. Okay.
Okay.
Yeah. Any other question?
If I want more, if I want to solve more questions, where can I get them? The book?
Okay, yeah, this is an excellent question too. I have uploaded, I think, study material here. Okay, you can find major 1 and major 2 questions. Okay, and as well as the finals, some terms, and also there is the ungraded homework. You don't have to submit them. You can try them and then compare the solution to your solution. So here, convert the following numbers from the given base to the bases indicated. Okay, so from decimal, this one, to binary. We haven't covered the fraction yet. Okay, but you can do the integer part. from now. Okay, you want to convert it to binary, octal, and hexadecimal. Okay, and then convert this binary to decimal. We have done this already. To octal and hexadecimal, we still have to do it. Okay, but you can do it in a twisted way. Okay, the solution is available, by the way. If you want, you can see the solution here, but I advise you to try it yourself first and then look at the solution. Okay, you get that?
Yes.
By the way, if you come late to the lecture and you miss the attendance, just write down your name and ID and mention that you missed the attendance in the chat area, okay? So that I record you as late, okay? All right, I'm done here. If you have any other question or otherwise you can leave. Let me stop recording.